Hello students, welcome you all to next session regarding discussion on the problems on the second part, that is the analysis of the turbo machines. In the last sessions we have studied regarding the theory part and the key points, how to draw the velocity triangles, how to write the equations, and in today's session we will be discussing regarding how to solve the problems by sketching the velocity triangles and finding out the various parameters which are asked in the questions. If you have any doubts, you can send me an email to the email IDs which are visible on the screen. Also, you can send me a WhatsApp message also, students. Now, let us begin the today's session regarding discussion of the different types of problems on turbo machines. So the first question which is visible on the screen, you can see here is, it is said that the combustion products approaches an axial flow turbine rotor with an absolute velocity of 550 meters per second and a direction of 18 degrees from the wheel tangent. The mass flow rate is 60 kg per second. If the absolute velocity at the rotor exit is axially directed and the blade speed is 300 meters per second, find the power output and the degree of reaction. These are the things which are asked in the question. So before we start the sketching of the velocity triangles, let us find out the given points in the question such that we can solve the problems very easily. If you go on observing things step by step, he says, first it is approaching an axial flow turbine. So if it is an axial flow turbine, you know that the tangential speed U1 at the outlet, at the inlet is equal to tangential speed at the outlet, which is equal to U. This is the first thing which is given in the question. Then he says there is an absolute velocity of 550 meters per second, which means these products, they are approaching the turbine inlet with an absolute velocity of 550 meters per second, which means V1 is equal to, it is the value of 550 meters per second. This is the value of 550 meters per second, and particularly this particular value and this velocity of 550 meters per second, it is approaching with a degree of 18 degree from the wheel tangent, which means to say that suppose if this is my rotor wheel, which you can see on the screen which I have drawn here, and suppose I say that this is the nozzle from which the combustion products, they are coming out and they are impinging, that is they are striking the turbine blades. So at this tangent we call this as alpha 1. This is nothing but alpha 1 is equal to 18 degrees. So this is alpha 1, which is equal to 18 degrees from the wheel tangent as per his question. Then the mass flow rate he has given as 60 kg per second, which means that is your m dot. Then he says if the absolute velocity at the rotor exit is axially directed, he means to say that when the outlet products are going out of the rotor exit, they are axially directed, which means the absolute velocity at the exit, that is V2, if it is axially directed, then it becomes equal to Vf2. Vf2. Then the blade speed is 300 meters per second. The blade speed is thing, but it is with respect to U itself. He has given the blade speed as 300 meters per second. You need to find out the power output P as well as the degree of reaction R. These are the given conditions. The only change here is the shape of the velocity triangle, where he has said that the axial velocity, it is the absolute velocity at the outlet, it is axially directed, which means the outlet velocity V2, it is overlapping on the flow velocity at the outlet as Vf2. So both are overlapping on one another. So when both are overlapping on one another, obviously even the tangential velocity of the absolute component, that is Vu2, it is also 0. Let us see how we get the particular sketch. So as I told, if I draw this as my inlet velocity triangle in this particular fashion, let us draw the inlet velocity triangle here. Suppose this is my inlet velocity triangle, which you can see here. This is V1, this is alpha 1, This is VR1. This is beta 1. Then I have this as VF1. From V1 to VR1, I have the tangential speed here. As it is an axial flow turbine, it is U itself. Then V1 to VF1, I have this as VU1. It is also moving in this direction. This is for the generalized structure of an inlet velocity triangle. Similarly, if I draw for a generalized structure of an outlet velocity triangle, it is like this. Here, this is VR2. This is beta 2. Then we have VF2. Here, I have V2. Then from V2 to VR2, I have the tangential speed U, and this as VU2 in the opposite direction. This is the generalized structure of the outlet velocity triangle. This is outlet velocity triangle, generalized figure it is. Similarly, this is the generalized figure of an inlet velocity triangle. For the inlet velocity triangle, he has not given any more conditions in the changes, but for the outlet velocity triangle, he has termed one particular condition. That is, he says that if the absolute velocity at the rotor exit is axially directed, so absolute velocity at the rotor is this one, exit is this one, V2. He says it is axially directed, which means it is overlapping on this one. So when it is overlapping on this one, the new velocity triangle, it will be in this particular fashion. That is, this is invisible, which means it is moving and overlapping on VF2. So therefore, it is just a right angle triangle, outward velocity triangle, where V2 is equal to VF2. And obviously, when V2 is equal to VF2, then here we don't have even our VU2 here. It becomes equal to 0. And your U is from here directly. Therefore, your VU2 in this case, it is equal to 0. Remember, if you draw the velocity triangle correctly, half of your problem is solved. Only the thing is, you need to find out the velocity terms using your trigonometric functions, get the answers which they have asked in the question. So let us move ahead now. We are noting down the given terms. As I said, is the axial flow turbine, tangential speed U is equal to 300 meters per second, which is given. V1 is 550 meters per second, alpha 1 is 18 degrees. Then mass flow is given. This is the inlet velocity triangle, as I said. Similarly, this is the outer velocity triangle. You can see here V2 and VF are overlapping on one another, therefore VU2 is 0. Now find out the trigonometric functions. And another important thing in the question which he has already said here, that he has said that it is an axially directed rotor, exit is axially directed, which means these are the conditions, that is VF1 is equal to V2 is equal to VF2, and even VU2 is equal to 0. These are the conditions. Now with these conditions, we start the solution of the given problem using which term which has asked, that is the power term M dot E, or E is nothing but it is U delta VU by GC. Delta U is VU1 minus VU2 by GC, as it is a turbine. So U1 VU1 minus U2 VU2 by GC, or it is from the inlet velocity triangle. We need to find out the terms of the values, that is VU1. Alpha 1 is given to us. Then we can take the help of the trigonometric functions and sin alpha 1. So if I use this particular inlet velocity triangle, that is, you can see here I am shading with the black color this velocity triangle, then V alpha 1 is equal to, it is V of 1 by V1. So on simplification, I get the value of V of 1 as 169.959 meters per second. As we have said that it is axially directed, so it is equal to V2, which is equal to V of 2, which is already mentioned in the question. Similarly, for the same velocity triangle, I prefer tan alpha 1, where I will get the value of VU1 using this particular trigonometric function. And I write that VU1 is equal to 521.944 meters per second. The next, P is equal to m dot u V1, as we know that in the inlet, in the outer velocity triangle, you can see here that it is mentioned that VU2 is equal to 0. So therefore, my power equation becomes P is equal to m dot u V1, and on substituting the values, I get the answer of power as 9,394.992 kilowatts in terms of kilowatts. Degree of reaction equation, already you know, you can write the degree of reaction equation in this form. It is R is equal to E minus V1 square minus V2 square by 2 GCI V. E is nothing but, if you observe this particular equation, this is U V1, it is nothing but it is energy E itself. So directly you can get the value 300 into 521.94, whatever the product is, that is nothing but representing the term E. V1 is already given in the question to us. We have found out the value of Vf1, which is equal to Vf2, which is equal to V2 as per the given statement in the question. So automatically you can substitute the values here of V1 square and V2 square. And on simplification, I get this answer as I said, first I will find the value of E. So I got the value of V in terms of kilojoules. Similarly, I find the value of R, and on substitution and simplification, I get the value of degree of reaction as 0.1258. Similarly, another next problem. He says here clearly that there is, at a stage of an impulse turbine, the mean blade diameter is 0.75 meter. At a stage of an impulse turbine, the mean blade diameter is 0.75 meters. Then he says its rotational speed being 3,500 RPM. As he has said, the absolute velocity of the fluid, it is discharging from the nozzle inclined at 20 degrees to the plane of the wheel, 275 meters per second. If the utilization factor is 0.9 and the relative velocity at the rotor exit is 0.9 times that of the inlet, find the inlet and exit rotor angle. Also find the power output from the stage for a mass flow rate of 2 kg per second and an axial thrust on the shaft. Students, when we start extracting the data from this particular problem, first he has said that there is an impulse turbine. So always we know that for an impulse turbine, the degree of reaction R value is equal to 0. And the next case is VR1 is equal to VR2. By default it is. But if he has given any one relation between VR1 and VR2, then you cannot accept this relation directly, that is VR1 is equal to VR2. Also, beta 1 is equal to beta 2. So these are two conditions, that is you can see on the screen, that is VR1 is equal to VR2. If he has not mentioned regarding anything about the relative velocity at the outer inlet, you can take these conditions. But if he has mentioned that some value of outlet is equal to some constant term of inlet, then you can't accept this one. Then that time it doesn't satisfy this particular conditions. But this value is there for impulse turbine. R value is equal to 0. Then he has said the mean blade diameter term. Always remember, if he has said the term the mean blade diameter, it is nothing but a symbolic written as dm, which is a short form of the tangential speed u, and it is almost equal to an axial flow turbine itself. The mean blade speed means related to an impulse axial blade turbine, it is dm. Then he has said a rotational speed, that is the value of n is given to us in the problem, 2500 rpm. The absolute velocity of the fluid discharging from a nozzle. So if I say that this is my nozzle, then the fluid which is coming from the nozzle, it is being discharging from this nozzle, and this particular nozzle, it strikes this rotor with some angles. So this is nothing but your alpha 1. So this alpha 1 is nothing but it is the value of 20 degrees to the plane of the wheel with a velocity of 275 meters per second. That is nothing but V1. Utilization factor is given, that is epsilon. Then relative velocity at the rotor exit is 0.9 times that of the inlet. So what do you, this is the very, very important term. Relative velocity at the rotor exit is 0.9 times that at the inlet, which means that is the term rotor relative velocity at the rotor exit, that is VR2 is equal to 0.9 times of VR1, which means that VR2 is not completely equal to 1. It is equal to some value of constant term, that is 0.9, which obviously means beta 1 and beta 2, they are not the same. When this is the case, beta 1 and beta 2, they are not the same. You have to find them differently. That is the reason you have to find out beta exit angle and rotor angle separately. Also find out the power output from the stage, that is power P, and he has given axial thrust, that is Fa. So as we have discussed, draw the generalized structure of the velocity triangles, because he has no more modifications in the sketch of velocity triangles according to the given statement. I will note down the given data and the velocity triangles. This is the sketch for the inlet velocity triangle, similar to the sketch for the outer velocity triangle, which you can see here right now. Now, once we have done the sketches of the inlet and velocity triangles, we have to find out the velocity terms using our trigonometric functions. So let us begin with the inlet velocity triangle and the given conditions in our problem. Tangential velocity already has given us the mean diameter, that is u is equal to pi dm by 60. On substituting the value of dm and n, I get the value of u as 137.462 meters per second. So in this inlet velocity triangle, I have shown here that this is the value of u1, but here as he has said it is a mean diameter. So u1 is equal to u. Similarly, u1, u2 is equal to u only. So almost it is a case of an axial flow turbine itself. Then he has given a utilization factor epsilon. So epsilon equation we know. Epsilon equation generally we write this epsilon as epsilon is equal to V1 square minus V2 square divided by V1 square minus R of V2 square. So already in the question he has mentioned that it is an impulse turbine, which means R is equal to 0. So if you substitute R is equal to 0 here, epsilon is value is given in the question, V1 value is given in the question, then you can find the value of V2. So using this particular equation and the given condition, on simplification and substituting the values, I get the value of V2 as how much? 86.96 meters per second. From the inlet velocity triangle, you can take the help of your trigonometric functions, that is the sine, cos, or tan, and get the values of Vf1 and Vu1. So right now what I will do is I will take the help of this trigonometric function for this particular triangle, which I am highlighting with the black color for the inlet velocity triangles, which you can see in the figure, where I am having an angle of alpha 1. So I can use sine alpha 1, I will get the value of Vf1. Similar, if I make the use of tan alpha 1, even I will get the value of Vu1. So I use the value of sine alpha 1. Sine alpha 1 is equal to Vf1 by V1. V1 is already given in the question. Alpha 1 is given, and on simplification, I get the value of Vf1 as 94.05 meters per second. Similarly, for the same velocity triangle, I take help of the trigonometric function of cos alpha 1, no problem. I'll get the value of Vu1, and then what I can do is I move for the inner side. Now in the inlet velocity triangle, please observe your stones. I'm highlighting with the blue color. This particular velocity triangle, it is a right angle triangle. Already Vf1 is found out, and this particular length is nothing but it is Vu1 minus u. V1 is being calculated, U is calculated, so I can find the value of VR1 using my Pythagoras theorem. That is VR1 square is equal to V of 1 square plus V1 minus U square, U whole square. So on substituting the values and on simplification, I get the value of VR1 as 153.218 meters per second. Then the remaining angle is beta 1. Tan beta 1, I can take the help of tan beta 1 and I get the value of beta 1 as how much? 37.86 degrees. So for inlet velocity triangle, all the angles and all the factors we have calculated. Similarly, we find out the factors, velocity terms, and all the angles for the outlet velocity triangle. But in the outlet velocity triangle, their own relation has been established saying that if we want to find out the value of VR2, you should make the relation which is given in the question, that is VR2 by VR1 is equal to 0.9. Let us see how it can be done. So outlet velocity triangle VR2 is equal to 0.9 VR1. So we get the value of VR2 as 137.896 meters per second. The value is given to us. So you know the value of U. We don't know the other values, V2, alpha 2. So using this method, that is, we can go for applying the cosine rule. And please observe the cosine rule is applied for this particular triangle in the outlet velocity triangle. I am highlighting with the black color ink. This is the outlet velocity triangle. I am applying the cosine rule, and for cosine rule, we write it as V2 square is equal to VR2 square, the other sum and square of the other two sides, VR2 square plus U square minus 2U into VR2 cos beta 2. So already I have said that here U2 is equal to U. Similarly, U1 is also equal to U itself. Already we have discussed. So directly I am writing the equation as VR2 square plus U square minus 2U VR2 cos beta 2. So on substituting the values of VR2, U2 and the value of V2 which we have already derived from our utilization factor equation, I will get the value of beta 2, and on simplification I get the value of beta 2 as 36.82 degrees. Okay. Then using the trigonometric function of sine beta 2, so that is now I apply this trigonometric function for this particular outlet velocity triangle. Please observe here, which I am highlighting with the black colored ink. This is the outlet velocity triangle. I will be finding sine beta 2. Sine beta 2 is Vf2 by U2 plus VR2, or what you can do is, apart from this, you can go for this method. Sorry, sine beta 2 is nothing but Vf2 by VR2. Sorry, students, Vf2 by VR2. So you know the value of beta 2, you know the value of VR2, you can find the value of Vf2 from this equation. So you get the value of Vf2 as 82.798 meters per second. Then I go for the cos beta 2 equation, and the cos beta 2 again using the same outlet velocity triangle, that is this outlet velocity triangle itself. I can write cos beta 2 is equal to VU2 plus U divided by VR2, and on substitution and simplification I get the value of VU2 as minus 27.1309 meters per second. Students, observe here carefully. Here if you observe, the value of VU2 is negative, which means whatever the sketch you have shown, the direction of VU2 in this particular sketch, it is should be in the opposite direction. Then only you will get the correct value sketch. The flow will be in the correct direction. So with this outward velocity triangle sketch, we had assumed until we got the value of VU2. So if the VU2 value was positive, then the sketch was right. As the VU2 value is negative, then we need to shift this absolute velocity V2 to the other side, that is to the other side here. This is the other side, and the new VU2 will be, it will be shown in this direction, the arrow mark. This is our new VU2. So here this negative sign is indicating the direction of the VU2, but the magnitude remains the same itself. Please keep in mind. Please keep in mind, the value of VU2 is representing the magnitude, and if it is a negative value, you should change the direction of V2 and redraw the outward velocity triangle once more. then only the marks will be awarded to you. Otherwise, you lose the marks. So I redraw the velocity triangle once more, and then this is the outer velocity triangle which we had assumed initially. So as I have said, negative sign is indicating that VU2 is in the direction of U. So therefore, the magnitude remains same itself. Then the new outer velocity triangle, if you observe, see, this is the new outer velocity triangle. If you observe here, this V2, it is shifted to the other side, which you can see here in this particular sketch. This you should draw compulsorily. Then only marks will be awarded to you. So now with these conditions, we have the rotor inlet and outer triangles, power output m dot E. E is nothing but U1 VU1 minus U2 VU2 by GC. As it is a mean blade diameter, it is U into VU1 minus VU2 by GC. You have the values. And one more important thing what to do is, while substituting the value of VU2 here, substituting the value of VU2 here, what you do in the hurry is, you try to put this negative value. No, the negative value is just intimating the change in direction of VU2. The magnitude remains same. So it is only 27.1309 here in this. Please note this point. So on simply substitution and simplification, I get the answer in joules as 3172.77 joules, or it is 31.792 kilojoules. Then the another part which is left is regarding the power. So power, we get it as 63.584 kilowatt, and the axial thrust which we are left is it is nothing but the difference between the VF1 minus VF2 with the mass flow rate in the form of newtons. So the equation is Fa is equal to m dot VF1 minus VF2 by GC, and the equation substitute the values, and we get the equation as 22.674 newtons. So these are some of the problems. Another some 2 to 3 problems are there which I will be discussing in the next session, students. So these are some of the problems which you can see, especially on the axial flow of turbines. So in the next session, we'll be discussing some of the problems with respect to the radial cases. So in the radial cases, we'll be knowing, or with respect to the inlet and our outlet, how the shape of the velocity triangles can be changed. Thank you, students.